The nature of dark matter, the invisible substance that makes up the majority of the mass in the universe, is one of the greatest mysteries in modern physics. For decades, scientists have been looking for clues about what dark matter is and how it behaves, but they have yet to find direct evidence of its existence. They have instead deduced its presence from its gravitational impacts on ordinary matter, like as stars and galaxies. However, not everyone believes that dark matter exists. Some alternative hypotheses argue that dark matter is unnecessary and that the observed occurrences may be explained by changing the principles of physics or gravity. These theories contend that dark matter is a myth and that we must reconsider our knowledge of the cosmos. But how can we put this dispute to rest once and for all? Is it possible to test whether dark matter exists? A new space telescope, however, may be able to achieve just that. Euclid is its name, and it has just opened its eyes for the first time. Euclid is intended to investigate the dark universe in extraordinary depth and precision by charting the distribution and evolution of dark matter and dark energy throughout cosmic history. Euclid will aid us in determining if our existing ideas of physics and gravity are valid or need to be revised. We'll look at how Euclid works, what it's seen so far, and what it wants to uncover in the future in this video. Let's explore the dark side of the universe with Euclid. Euclid is a European Space Agency mission that was launched on July 1, 2023, with the goal of studying the dark universe, which is made up of dark matter and dark energy. These are mysterious substances that account for around 95% of the total mass and energy of the cosmos, yet we have no idea what they are or how they function. Dark matter is an invisible kind of substance that, through gravity, ties galaxies and clusters together. On the other hand, dark energy is an unknown component that causes the universe's expansion to accelerate over time. Euclid expects that by researching these events, he will be able to shed light on some of the most pressing cosmological concerns, such as the universe's creation, evolution, and fate. Euclid has two strong cameras on board to accomplish this: a visible imager and a near-infrared spectrometer and photometer. These cameras are capable of capturing photos of billions of galaxies spanning more than a third of the sky and a distance of 10 billion light-years. That means they can observe how the universe seemed only a few billion years ago. Euclid can map the distribution and evolution of dark matter and dark energy over cosmic history by measuring the shapes, locations, hues, and distances of these galaxies. But how do these cameras function? To collect different wavelengths of light, they use various sorts of detectors. The VIS camera records visible light using CCDs, charge-coupled devices, which is the same technology used in digital cameras and smartphones. The NISP camera records near-infrared light using H2RGs, hybrid 2 readout gratings, which are invisible to our eyes but can pierce dust and gas in space. The NISP camera also has a unique function in that it can split light into its spectrum using a grism, which is a prism and grating combination. This enables it to measure the redshift of galaxies, which is a measure of how far their light has been stretched by the universe's expansion. Knowing the redshift allows us to calculate how far away a galaxy is and how quickly it is moving away from us. These cameras have numerous advantages over other types of space telescopes. They have a very big field of view, for example, which means they can cover a larger region of the sky in less time. They also have a very high resolution, allowing them to see more details and fainter objects, as well as a very broad wavelength range, allowing them to observe more sorts of galaxies and stars. However, these cameras confront significant difficulties. For example, they must contend with extremely high amounts of radiation in space, which might harm their detectors and electronics. They must also deal with extremely low temperatures, which can impair performance and stability, and they must properly calibrate their images, which involves correcting for any distortions or mistakes induced by their optics or environment. Euclid's cameras were tested and calibrated before and after launch using various methods and devices to address these issues. They were subjected to extensive simulations and experiments on Earth prior to launch to assure their quality and accuracy. They were, for example, placed in vacuum chambers that simulated space conditions. They were also exposed to different light sources that simulated the stars and galaxies they would observe, and they were calibrated using special devices that measured their sensitivity, alignment, focus, distortion, noise, and other parameters. They were also checked and calibrated after launch using actual space observations. They collected photos of well-known stars and galaxies, for example, to use as reference points for their measurements. They also photographed empty areas of the sky to serve as backgrounds for their subtraction, as well as photographs with varying exposure periods and filters to serve as inputs for their analysis. The complexity and diversity of their devices contributed to some of the challenges they experienced during these testing and calibrations. They had to account for the effects of temperature changes on their detectors and optics, as well as any shifts or drifts in their pointing or focus caused by vibrations or thermal expansion, and they had to remove any stray light or cosmic rays that could contaminate their images. Some of their triumphs during these tests and calibrations were due to the performance and dependability of their devices. They validated, for example, that their detectors and optics were performing as predicted and within their specifications. They also demonstrated that their cameras were ready and capable of achieving their scientific goals by verifying that their images were sharp and clear and matched their simulations and forecasts. Following these testing and calibrations, Euclid's cameras were able to capture their first images from space. These images were made public on July 28, 2023, and they depicted some incredible vistas of the universe's stars and galaxies. Let's look at a few of them to see what they show. The first image we view is from the VIS camera, and it depicts a region of sky with approximately 100,000 stars and galaxies. The colors in this image reflect varying levels of brightness, with blue being the most visible and red being the least visible. This image has a resolution of roughly 0.1 arcseconds, which implies it can separate objects as near as 0.1 seconds of arc, or about 500 meters apart at a distance of 10 billion light-years. This image is noteworthy because it demonstrates the VIS camera's power and precision. It is capable of capturing images that are significantly deeper and sharper than those captured by past or present space telescopes, such as Hubble or James Webb. Hubble, for example, has a resolution of around 0.05 arcseconds, but a field of view of only 0.01 square degrees. The resolution of James Webb is roughly 0.1 arcseconds, but the field of view is about 0.002 square degrees. Euclid can combine great resolution with a vast field of view, making it perfect for mapping the universe's big-scale structure. Euclid will collect additional images like this in the coming years and use them to explore the dark universe in unparalleled detail and accuracy. Euclid will help us comprehend some of cosmology's most fundamental riddles, such as how the universe began, evolved, and will end. Thank you for watching, and if you liked it, please like, share, and subscribe to our channel to see more videos like this one. Stay curious and keep discovering until next time.